Okay. Gonna turn off this for now. See what I can do here. Where'd it go? That's where it is. Hello, everybody. Class has started. I'm still getting a little bit set up here. But we're good on continuing on with our material. I'm going to talk about the assignment a little bit, or the one that's due tonight and late deadline tomorrow, because I have gotten some questions already from you guys, and I obviously did not cover that in class last week. So I'm going to address those and maybe put just a little bit of code in front of you that can hopefully help you move past that if you happen to be stuck on some of these errors. So hopefully that will be good. Today we're going to start recursion. We're going to start recursion. And so it's about to get fun. That's all I'm saying. Next week, we're going to do linked lists and maybe a little bit of exception handling. Linked lists might be one of the most complicated subjects in CS202. So not to scare you, I'm going to do my best, and I'm here to help you with all of that. I'm going to give you guys a ton of code for that, so you're always going to have something to reference. And I'm going to comment it as much as I possibly can, but I just want to let you know that so that you pay attention. Are there any questions that you guys immediately have? Maybe just actually hold off on that. Just keep them in your mind if you have them for assignment 7. As I kind of discuss I think I have 3 things here. Yeah, three things that I want to talk about. So maybe I can answer some of those questions you might have real quick first to start. And if I don't, then please go ahead and throw your question at me, and we can see if I can address it here at the beginning of class. Assignment 8 will be going up tomorrow. I will not cover it today. There is a video surrounding assignment 8, so I can provide that link. Additionally, I will briefly go over it on Wednesday. But just so you know, assignment 8 will be going up tomorrow. And that one looks like it's going to be a fun one as well. And when I say fun, I think like actually fun. I'm not saying that it's scary. I'm saying that it's enjoyable. As opposed to just sorting the garbage or overloading operators for a matrix class. This time we get to do something that's a little more computer science-y, I guess. So the first thing I'm going to do is just pull up assignment 7 skeleton code. And then I'll make the screen available to you guys. I just want to make sure I can find it, and it looks like it's here. All right. Oh, I messed that up, guys. Whoops. I'm so sorry. Oh, I'm so sorry. All right, well, that's why we're here in class today. All right, so here is the bucket. Here is the bucket.hpp. So I had provided this class thing here to you. And then additionally, when I had uploaded it, we didn't go over how to do this, and I had made a mistake here. I think most of you know how to correct this, but if you haven't yet, on line 30, please put in your type here. And I'll fix that, okay? So I did forget that. I'm always making mistakes, but just so you know, that's how we fix that. Because we need to tell that this constructor is in the bucket namespace, but not just the bucket namespace. It's specific to the type that is tied to this template here. And so everything in here should be straightforward. If you are kind of referencing the dynamic array that we went over for pointers, you should be able to kind of get maybe the insert going on here. Oh, well, you actually don't have to code anything for the insert because it's a pure virtual. But maybe for these kind of things, I know that I've hopefully done one of these in front of you before. If not, you did it for the assignment last class. And this one's really simple, right? I can even just put it here in maybe subcode. And what you're really just going to return this array here, you're really just going to return the array located at I. But since array is private, if we overload this bracket operator, then we can totally reference things like this. If we were to say have a bucket B, and then if we see out something like BI, then it will act like a vector. You recall with vectors that we can use this bracket, and that's because the bracket operator is overloaded in vector class. So that's really all it's doing. So take note of that, screenshot, whatever you'd like. That one's really easy. You may wish to add some additional checks just to make sure that this index is not below 0 or it's not greater than the size of the array, greater than or equal to the size of the array. But other than that, it's really just this line of code, right? So yeah, if I haven't done the brackets, then you have that there. And then the rest of this stuff is pretty simple. You can do whatever sort you'd like. If you want to use this swap, you can for your sort. I'd recommend doing it. Having the swap function is always nice. And these should be pretty straightforward. Make sure that you deallocate this array in your destructor. But other than that, right, you can just go in here and type away array equals something, etc. So we actually had no problems here, but the first problem that we really notice is when we get to either the dynamic bucket or the static bucket. So say we're in the static bucket and we want to inherit. So recall that this is a template type. So we'll do type name T here, if you'd like. And then we're going to do class static bucket. And then we're inheriting, right? So we're going to publicly inherit from this bucket class. So can anyone tell me what? So VS Code is not yelling at me yet, but it will. And can anyone tell me what I need to add here? For those of you who've, let's see, Sibe says, oh yeah. So Sibe caught me up here with my error when I had typed this. When I had done this, he's correct. I would have needed to do something like this. So CBA, you're 100% correct on that, and I apologize. That was just a little bit of pseudo. But on that same line, coming back to this thing, Is there anything that I need to add here? And if I helped you answer this question, please throw it in the chat. And if you think you know, please tell me, because I think that would be helpful to everybody. Yeah, exactly. So T. Peter got it. So we're inheriting from bucket, but what bucket? And the answer is a bucket that's associated with this type. So in order to correct any compiler errors here, you're going to want to put that T there to say, hey, this bucket is going to be the same type as this static bucket. So that's the first thing when it comes to inheritance. And I did not cover that last class, so now that we've gone over that, here it is. Now the second thing that people are having some problems with is sometimes if you look in the garbage processor, and notice that it's mad at me right now, and that's just because I haven't coded these classes up yet. But it'll say, hey, this is an error. And it says you cannot instantiate a static bucket because of that it's abstract. Now, the only thing that's abstract in this file is bucket. The only class that's abstract is bucket. So the static bucket should not be abstract. And so you're going, what the heck? Why are you yelling at me? Because I thought that I got this right. I had made a mistake in the PDF, so let me find it. Here it is, yep. So this is totally my bad, all right? And so if you were just being consistent, this is totally my bad. Notice here that I have a capital I. Notice I have a capital I here. Now, if we go look in the bucket class, this insert is done with a lowercase I. Which means that a capital I insert and a lowercase I insert are actually different functions, okay? So if you were in here and you had typed, what I normally do is I just go here and copy it. But that's just me. But if you're typing it out and you had typed out this, and then in here you got some code going on, this is where you're going to get the abstract class error. And it will be pointing at this. It's going to say, hey, this is bad because static bucket is abstract. So in order to fix that, all you have to do is come in here and make this make sure that it's a lowercase I, which then specifically will override this function here. Okay? Are there any questions on that? Please let me know. Once again, this is a mistake. This needs to be a lowercase I, not an uppercase I. And if you're ever in doubt, just check the bucket class. Okay? Here it is. So that's thing number 2. Thing number 3 is some of you guys will probably try to access this array at some point, right? If it's a static bucket, I think I said the max size is equal to 20 or something. Now, look what it's kind of saying unknown here. It's saying that this is unknown. Now this array class, this array belongs to the bucket. Here it is. And it's under protected. So you should be welcome to just access this. You should 100% be welcome to just access this thing. Except there's a problem. And it's that we're inheriting from a templated class. And so templates make this very picky. They're very picky about this. And they say, hey, what is this array associated with? And so you specifically have to make sure that this array is coming from this type of bucket here. So you can do a few things, I think. The first one, the easiest fix, is just use this. This one is probably the nicest way, in which it will force the compiler to just reference whatever object we're working with, and then it will grab this array. If you don't want to do that, you're going to have to use a namespace, a scope resolution operator, and you specifically have to include the template type with it. Now I'm pretty sure that'll fix it, and this might work as well. But I'm not sure about this one. I think this will work. I think this will totally work because of the template here. But if it doesn't, then just use this. And the reason you have to do that is because we're associating this template type with this array. So once again, you cannot access things like array, and you cannot access things like size unless you use either this, the bucket T, or maybe the static bucket T. And this goes for the dynamic bucket as well. And so I did say that this is the third thing. So I'm gonna tack on. No, that was the third thing. All right, so we're good. So those are the three things that I'm gonna mention here for you guys. And look, I've kind of even helped for some of those who haven't started yet. I've even kind of given you here a little bit of a hint just how to do this. So do you guys have any other questions in regards to assignment 7? Before I move on today into the recursion stuff. We're pretty much done here with templates. They may pop up in a future assignment, definitely on the test though, and we will have a review day. Let's go ahead and look at the syllabus. Why not? So it looks like we're here right now, in week 10 about. And so it looks like we've got about 3 weeks here until we have midterm 2. So we will definitely have templates, operator overloading, and virtual stuff appear on this midterm here. And like I said, we'll always do a review day. Here it is. I put it in the syllabus, so you can expect that. So I'm going to go ahead and move on. And if anyone's still typing something out, feel free to just type it out. And I'll go back. I don't mind. So let's close this. I don't want to save that. Does anyone have any idea what recursion is? I suspect that you may have heard it before. And if you do, in layman's terms, do you want to kind of tell me what it is? Maybe I'll get my notes started here. If you want, of course. If you don't know what recursion is, that's fine. I'm going to show you that silly Google joke. Everyone loves the Google joke. So let's go to Google. Let's go to Google here. Type in recursion. And here's the joke. The joke is, it says, did you mean recursion? It looks like I spelled it right. It looks like let's see. T. Peter says, kind of looping from front to back to get an answer. I kind of like that. You're along the same lines. You're along the same track. Now here's the Google joke. Notice I spelled these exactly the same. So no matter how much I do this, it's just going to take me back and back and back and back and back. And so we'll talk about that. But what recursive is a recursive function is a function that is a function where the definition includes a function call to itself. And I'll take out this tab here and we'll just do a space. Maybe I'll make this full screen here. Okay? So that's really it. That's the main definition of this. And what I'd like to communicate to you guys is there's no really specific way to develop. I mean, there may be a method out there, but recursion is to think recursively, rather, is kind of something that we have to train ourselves to do. Now, so I'll sidetrack a little bit, and I'm just going to talk about some conversations that I've heard from some other professors in the UNLV Computer Science Department. A few years ago, pretty recently, Google, in conjunction with University of California, Santa Barbara, right, UCSB, they had achieved quantum supremacy. I don't know if you remember seeing that article, but they had run a program on a quantum computer. And the problem they solved, it wasn't like a world-fixing problem. It was kind of a simple example problem. But it was a numbers problem that on a standard computer would take, I think, 10,000 years for the computer to solve it. So that computer would be running CPU cycles for 10,000 years, trying to solve the problem, and that's when it would be done. And so they had to kind of redo that problem in some quantum code, and then run it on the quantum computer, and I think it solved it in 40-some seconds. And so when it comes to quantum computers, from what I've read, the best way to code a quantum computer is using recursion. And so there's some discussion as to get students in, say, elementary school, when they should get some early kind of computer science-y classes. And in those, they will learn to think recursively. I may have spelled this wrong. Let's check Google. Why not? Yeah, it's okay. It seems okay, right? Yeah. And so we really don't know what to think recursively, what that means exactly yet. But what I'm going to say is it's going to be a little, maybe for you, maybe not. It's going to be a little bit difficult to kind of rearrange your brain to think about things like this. But I promise it's super cool, and we're going to have a good time. Right now, we think iteratively. Iteration. We think in iteration, so using, iterative. I don't even know if that's a word. It probably is, but this is loops, right? Now, Alan Turing, this is not going to be on your test, okay? I'm just giving you some history. Proved, and I'll just tell you kind of in, I guess, millennial terms who this person is. If you ever watched the movie The Imitation Game, or read a book, probably, or studied World War II at all, Alan Turing was the computer scientist who cracked the Enigma machine. Enigma is the code that the Germans had used to encode their communications. So I think what they were doing is they were substituting characters for other characters. And so the Germans were sending messages to each other over open communication, and the Americans could the Allies, I guess, they could intercept these communications, but they didn't know what they were saying because the Germans were using the Enigma machine to encode it. And so Alan Turing kind of created one of the first computers, a machine, to initially it brute forced. To crack Enigma. And supposedly the war was over significantly sooner. I think they estimated at least 2 years earlier. And Alan Turing was highly praised for doing this. And so what Alan Turing did was Alan Turing proved that anything that uses a loop in code can also be solved using recursion. Okay. Let me do some spaces here. I like doing the spaces instead. Do a little star there. So I'm just giving you a little bit of history. Now, some code has no loops. So if you take Dr. Miner's CS 326 course, perhaps even Dr. Ed as well, and if you take Dr. Pedersen, this would be a graduate class, but he does CS 789, which is multi-paradigm. Obviously, you probably won't do, some of you might, but this one most likely, 326. You will code in a program called Lisp. Has no loops. Now, some versions of Lisp might have loops. I'm not sure. You might also do Scheme. But these are coding languages that have no loops at all. And so you're actually required to do recursive thinking. And recursion is a big part of your career as a computer scientist. So we'll talk about a few things, recursion notes. So recursion is memory intensive. And in general, slower than looping. So, if recursion hogs the RAM, hogs memory, and is slower, why the heck would we use it? Why would we use it? Well, the truth is that many problems to be solved in a loop is extremely difficult for a programmer to think about. I've come across this, and sometime in the coming week, I will show you an example of a function that is hard to code using a loop. Last semester, I did this as well, but I was not prepared, and I showed all my students a very complicated program that I think no one understood. So this year, I've got a much better example of that. So we're just going to say that some problems are hard to think about using iteration. And recursive solutions are often, I will say, elegant, simple, easy to code. So that's why we use recursion. And what is the basic idea of recursion? So you always need to think about it like this. Always, 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 always. You have no other option to break the problem into smaller problems. Almost like building blocks. So in fact, some problems are able to be broken down into individual cases. And so you can handle each case individually. And then using recursion, we can kind of build a very nice solution to solving whatever problem this is. So I'll give an example of this. Let's talk about power. And even log can kind of be included in here. Power and log are almost the same function, actually. And if you know, a log is kind of like the reverse of power. In which if you take log base 2 of 8, just, I don't know the last time you guys saw log. Well, if you took log base 2 of 8, which in a way is 2 to the third, then you will get, should get 3, right? In which the log's idea here is to identify what the power is. And so these functions we're familiar with, given that we've taken some math classes before, probably. And so I'm going to give you the example of how to break it down. Let's say we take, we're going to do Microsoft Paint diagram, actually. I love using the whiteboard for this. So Microsoft Paint will serve as our whiteboard. And so let's go ahead and put some big things here on the board. Looks like I've already got big old text going on here. So we're going to call the power function, which will take some number and an exponent. I don't think this needs to be bolded. Okay. And so what does this correspond to? I don't really like that, so we'll do this one. That would be something like 2. Now I'll make a smaller number here. 2 to the third. That's a little too small, isn't it? That's a little better. Maybe we'll do 48. Yeah, that's nice. And so what does that look like? That will look like this. Power 2, 3, right? Does it make sense? And so what this is, in fact, is it's very simple. And I know that you know it. But this is 2 times 2. I'll do x times 2 times 2. Maybe make it bold. Right? So in a way, the 2's are the building blocks. The 2's are the, let's say what I said in the notes here, into smaller problems. So the 2's are the smaller problems. And so actually the power can be defined recursively. But let me kind of put this in front of you as well. 2 to the third, and I'm going to use this notation now, is equal to 2 to the second, 2 to the second times 2, which is also equal to, let's do it this way instead. 2 to the first, which is also equal to 2 to the first times 2 to the first times 2 to the first. Now, if you wanted to even take it one step further, that is equal to 2 times 2 to the 0 it's kind of where it gets a little crazy, because 2 to the 0 is equal to 1. CBay is giving me some knowledge here. Let's see. Oh, man, you're awesome. That's great. I will do that for the future whiteboards, okay? We're going to do some more whiteboards today. For now, I'm going to leave it like this, but thank you for that. I'm even going to screenshot it so I can reference it. Thank you, thank you. I always appreciate some knowledge. Yeah, I can't believe I call myself a computer scientist and I don't know how to zoom in on MOVA Xterm or do superscripts. Who am I? What qualifications do I have? And so let's kind of get to the code part, and then we're going to do a nice visual But the point here I'm making is that these are the smallest building blocks. You cannot go any smaller than this. But notice that 2 to the third is comprised of 1 of these, 2 of these, 3 of these. 1, 2, and 3 of them. So let's see what we got here. I haven't done my files yet. So we'll go ahead and do that real quick. Today is April. April. It's the 5th. It's a Monday. And we're going to get some notes going on here. I won't do that yet. And this will be power. So we're going to start with a nice small example here today. Nice CS135 program, as you might call it. Maybe we make that a little bit bigger. And so if we were going to do power as a loop, let's go ahead and do it that way. Loop power, which will take our int num and our int exponent, and we're going to do some looping. So the best way that we could think about it is pretty simple. We can say int return value will be equal to 1 to start. In a way, this is 2 to the 0. Or rather, num to the 0. And then we'll go through here and multiply it by 2 a few times. So I'll say for int I is equal to 0. I is less than whatever our exponent is, I plus plus. Or if you would prefer to do it this way, like I said, you guys need to be paying attention to how this works. When it comes to arrays, you don't have a choice. But when it comes to this, you can either do start at 1 and then go until you equal to 3, or you can start at 0 and go until you're less than 3, or the exponent. And then what we're going to do is we're going to take return value times equals 3, or no, not 3, but the num. And for those of you who are not used to that notation, okay, that's equal to this, right? Times the num. So same thing. And at the end, we can probably return our return value. So that's a nice loop there. And if we want to make sure that we know what's going on here, let's just do some couts to get us thinking along the lines here of what this looks like, to make sure that everything's right. So we're going to do 2 to the third. And let's do a few that we know. 2 to the 0 is a good one. Maybe even 8 to the 0. We can do maybe some nice big one here, 9 to the 9. We can do a 1 to the 100. And maybe we can even do, I don't know, it really doesn't matter at this point, right? What's one that we know? Maybe 4 to 2. 2 is always a good one. 2 to 6. So let's go ahead and give this a shot. Here we are on Bobby. All reliable. Oh, it's not going to be okay with that. All right, and let's just make sure. 2 to the third is definitely 8. 8 to the 0 is definitely 1. 9 to the 9 is probably this number. 1 to the 100 is definitely 1. And 2 to the 6 is definitely 64. So we got these right. So now let's go ahead and do a recursive function. going to take the exact same thing. And now what did I say here? I said in the notes, a recursive function is a function. Oh, sorry, folks. That's why we come back to the notes and we fix things. A recursive function is a function where the definition includes a function call to itself. What? What does that mean? Well, that means somewhere in here, we're going to do this. Now, I don't know what I'm going to call yet. Let's just kind of put num and exponent here. Now, as of right now, this will be infinite. I'm just letting you know, this is like an infinite loop. And this will just go off into oblivion. In fact, you'll get a Stack Overflow. So I'm sure a lot of you have Googled some coding questions before, and it takes you to this lovely website called Stack Overflow, which is like Reddit for coders, something like that, where you can ask questions and people will answer, or have discussion perhaps. And so Stack Overflow spawns from the idea that the stack, which we will talk about at the end of CS202 this semester, the stack is a memory construct in your computer. And whenever you call a function, we kind of put some memory on top of the stack. And so if we're going to infinitely call a function, it's going to place a function on top of the stack, and it's just going to keep stacking recursive powers until the stack runs out of memory. And then it's going to do an overflow. And then your computer will make a beeping noise, and the program won't work anymore. I'm kidding about the beeping noise. Maybe it will, but that's where it spawns from. And so our job is to break this down, define this function in a way such that we break it down into smaller problems. So there are a few things that recursive functions always need to have. Let's see. So recursive functions always need, it's either two or three things. So I'll make this edit as we go. But the first thing that we need is we need a reduction operation. That's how I like to call it. Sounds more English to me. Some people might say operator. What is the reduction operator? But you need some sort of reduction operation. And what does this do? This takes us a step closer to what we call to the base case. So while I'm typing out these notes and we look at our whiteboard here, can anyone tell me, let's maybe cross this one out just for now. Just by looking at this thing here, does anyone have an idea of what the base case would be? And I haven't defined the base case yet. I'm just basically, you know, what I've been talking about. I'm just wondering if anyone's got an idea of what a base case in this problem might be. So give me your ideas. And in the meantime, I will define a base case. Let's see. Seabay says, if it's even, you could always divide by 2 right and make it a power of 2. Yes. That's kind of the definition of even numbers. T. Peter says 2 to the 3rd, and I will say that that is the bigger problem. So 2 to the third is the big problem that we're trying to break down. And Red Rose says it's 2 to the first. And that is our base case, in which we're going to reduce the problem into these, well, I'll show you what the reduction operation is, at least in our code. But you are correct. The base case is this. The base case is this. It's 2 to the first. Or if you want to say 2 to the 0. I kind of crossed it out because I just don't want to get us confused. But this is going to be our base case. The base case returns, or in other words, the recursion stops. So on a base case, the recursion is going to stop. It will not continue. My face is probably in the way here. Face is always in the way. So it looks like maybe just 2 things. I guess if you wanted to say a call to itself. But we talked about that already, right? So let's talk about this. And CBay, you're talking about this. If it's even, it can be divided by 2. So I know you're already thinking about how we can do this. And I'm so excited for that. Because recursion is so fun. You might not think so at first, but it's really cool. So what we need to do is we need to break it down into a base case. So I'm kind of just going to wave my magic wand here, and I'm just going to kind of throw a solution out here. So usually we want to start with the base case. So CBay says, even if it is even, assuming if the number is even, it can be divided by 2. That is correct. So we could do it that way, but let's kind of look at the exponent here first. So looking here, let's look at what's changing from problem to problem. So first we've got a 3. So actually rather, notice that the 2's always stay the same, right? So the number is actually not changing. The number is this thing here. The number is actually not changing from, I guess we'll say, function call to function call. But what is changing? Here is the exponent, and the exponent is what's changing. And so where do we stop? Well, it looks like when the exponent is equal to 1. So we're going to call this our base case. So let's go ahead and put that on our whiteboard. And like I said, we could do it with 0 as well if we wanted to. I'll just keep repeating myself. I love doing that. So when the exp is 1, whoops, base case, in which we're not going to go any further. We're going to stop. This is our base case. And so that's what we'll check for here. We'll say, hey, is exp equal to 1? Question mark? So this is our base case. And let me just ask, looking at the whiteboard here, do you guys have, whoops, don't look at that. It's the same thing. It's the same thing that we're doing. But I'm working with my paint diagram here. So notice that it's 2 to the first times 2 to the first times 2 to the first. So if it's equal to 1, do you guys have an idea on what we will return? It's not a trick question. And it might be kind of obvious to some of us, and it might not be. But if, yeah, CBay nailed it, right? We're going to return whatever this is. That's exactly right. That's exactly right. We're going to return the 2. We're going to return that num. We're going to say, hey, we can't go any further, so we're just going to return num. Here you go. This stops our recursion. So now that we have our base case, we're going to prevent, well, we're taking step 1 into preventing Stack Overflow here. So we'll return that number. Else, now we don't have to put an else statement here, but I will because it's kind of easy to read. Because we're going to return from this if statement, the else is not required, but like I said, it's just easier to read. So else, we know exp is not equal to 1. And so now we have to take a reduction, and we kind of have to do something a little bit extra. So what we'll call is, I'm totally up for the class participation today. Does anyone have idea what the reduction is here? Yeah, so Sibe, you said if exp equals 0, the answer is yes, we could do that. And I'll do that, say, when we finish this one. But it'll be a little bit different, because if exp is equal to 0, so let me ask you this. If exp is equal to 0, what will we return? Because, and I want you to reference, yeah, exactly. Yeah, that's right. That's exactly right. You're kind of on top of things. So if it's 0, then we'll return 1, not the number. Red Rose says the reduction operator is exp minus 1. That's exactly right. That's exactly right. So recall that recursive power is an integer. It's an integer, so we can return it. This kind of notation might be a little scary to some, but get used to it, I guess. And we'll do plenty more examples here. But we're going to return a call to itself. Now there's one more step here that we need to take. Because in fact, this is just going to return 2. And so I guess I'll do my magic wand here. We're going to return num times the recursive power. So we're just going to take 2 times this. Now, if we made this 0, we could make this 1, and it should still work exactly the same, because notice that we're multiplying by the number here. So let's go ahead and do the tree. I wonder if you guys have been... let's see where we are. Have you guys been informed about trees before? This is going to be whiteboard 1. And so we're going to make a recursive tree real quick. So I'm actually going to close this and open a new paint, because sometimes I accidentally overwrite the old picture, and I don't want to do that. So let's make a tree. And this is our big problem up here. This is 2 to the 3rd right now. 2 to the 3. Red Rose asks, if we return 1 or 0, would that be the final answer since the other return is a call to itself? Yes, you're correct if I take out this thing. If I had taken out this thing, the way that this is now, my face is in the way. Of course it is. Sorry, everybody. Let's see if I can do this. Yeah, you understand. The way it is now, we would either return 1, or if it was this way, then we would return 2. But what I'm doing here is actually an operation on it. Now, the reduction operation is actually this. Maybe I should put that in some notes. But the exp minus 1 is what takes us closer to the base case. So when we talk about a reduction operation, it's taking us a step closer to the base case. And the base case is if exp is equal to 1 or 0. And so this is actually the reduction operation. This is just the definition of power in a way. It's 2 times 2 times 2 times 2 times 2. So this is kind of just part of the function. And this is the recursive call to itself. All right, now we're back. It's Monday. I'm a little rusty, but we should be good now, right? All right, everything's here. Okie doke. So let's continue on here with our recursive stuff. So we're doing this paint diagram here. And this is our big problem. And now we're going to break it down into these small problems. And so if we actually go take a look at that whiteboard one that we did, you'll notice here that the first thing that we do is kind of this thing here. I guess I'll take maybe... No, I won't do that. I'm just going to hover it with my mouse. It's this 2 to the second times 2 to the 1. In a way, that's kind of like what the recursive function looks like, right? So here we have 2 to the 1. This is 2 to the 1 times 2 to the exponent minus 1, right? So here we see that. We have 2 to the 1 times 2 to the whatever the exponent was minus 1. So to make a nice paint diagram for that, I'm going to copy this. Oh, and CBA, yeah, I said that I would do that, so I might as well. So I think I'll do 2 to the, let's see, Control Shift equals. So that's 2 to the third. And so what I said was we'll kind of go out this way. So if we're looking in terms of our function here, notice that I've got 2 to the first on the left side. It doesn't really matter, but we're going to do it that way. So if it's on the left side, then we'll take 2 to the 1. And then on this side, the right side, we'll take 2 to the 2. Okay. This is a tree. Does anyone know, and you don't have to, does anyone know what this kind of tree is called? And I'm sure there's plenty of names. Recursive tail tree might be one you've heard. That's not what I'm referring to. I'm referring into the number of leaves that it has. Does anyone have an idea what it might be called? And if you don't, that's fine, because I will be defining it later. And so now we're just going to break this down into another problem, right? Binary, yes. T. Peter got it. This is a binary tree. And it's a binary tree because it's got 2 leaves. The bi is for 2. If it were a trinary, I think that's what you call it. If it was trinary, it would have 3 leaves. In this case, it has 2, so this is a binary tree. So just to save myself a bit of work, I'm going to do this. And so then we're going to have this one here, which is 2 to the 1, right? So if we look here, you will see that it's this thing. And then we're going to take exponent minus 1. So that's going to be, from the 2, it's now going to be a 1. So let me erase that. Is my face in the way? No, it's not. So this is going to be 2 to the 1. And so recall that this, let me kind of move it to the left here. Recall that this, we're now at our base cases, right? So if we're at our base cases, we're actually going to return 2. So down here, we're going to return 2. Just going to put it, I'll maybe put it in blue. Here, we're going to return 2. And here, we're going to return 2. And what is the actual operation, not the reduction operation? The reduction operation is from here to there. And it's also from there to there. So that's the reduction operation. But the actual operation that we're doing is here. It's the multiplication sign. So all we have to do is take this, and this is going to be maybe a multiplication sign. So we're going to take these 2 leaves times these 2 leaves. And so this recursive problem is going to break out into a tree. And at the very bottom, when it gets to the end, it's going to take this 2 times 2. And then it's going to, so 2 times 2 is 4. And so then it's going to take 2 times, maybe I'll make this a different color. It'll take 2 times 2, which is 4. And then it will take 2 times 4, which is 8. And then it comes up here, and what's 2 to the 3rd is 8. So that's a recursive tree. That's a binary tree. So let's go ahead and test our function here to make sure that things work. Yo, please don't do that. Okay. So we should get the exact same output. It's nothing too crazy here. And it looks like I'm getting one problem that I made here, which it looks like for some reason I had that. And I think it's giving me a warning. And the warning is because it's outside of the... Really, the warning doesn't matter, but we'll just do it that way instead. And I did get a seg fault. Of course I got a seg fault. I wonder why. Oh, you know why I got a seg fault? Yeah, Red Rose nailed it, right? This is the issue here. Yeah, that's exactly right. That's our issue there. And so actually we ran into an issue here, and it would be better if we rather did this. This is a nice safe way. We'll do 0, and we'll just return 1. Now, this power is not going to work for fractions or negative values, but this is an integer version. So if we took 2 to the 1/2, which is square root of 2, we would get back 0 or maybe 1 anyway, because it's integer math. It's not decimal math, okay? So this is just integer power. This is not decimal fraction power. So this 0 here is what's causing the problem. And the reason is because we pass in a 0, and then if I had it as 1, the base case doesn't take, right? This if statement doesn't evaluate as true. And so then I'll come down here, and then I'll just take exponent minus 1. So it'll go to -1, and then -2, -3, -4, all the way until we stack overflow. So it's a good thing that we did that, because now we know, and we can now fix it. Now the seg fault usually happens when we dereference a null pointer. That may have happened, I'm not sure. But what I'm guessing is we stack overflowed. But I guess runtime errors are limited to only a few informative messages, such as seg fault. So, and there we have it. There we have it. So let me see. That's about right, right? 2 to the 3rd, 8 to the 0, 9 to the 9, 1 to the 100, and 2 to the 6th, right? Yep. So that was our first recursive example. Let's see if we can do one more quick one. Are we doing okay so far with the recursion? And if we aren't, then please let me know, and I can go revisit something. The next one that we're going to do is Fibonacci, and that's the most standard recursive exercise you'll probably ever hear in your life. And chances are we won't be able to finish it, just because I'm going to take my time here to make sure that we know what's going on. But I'll go ahead and just kind of code it out. I don't need to do this. And let's Wikipedia our Fibonacci sequence. Wikipedia. Now, I'm assuming you guys have heard about Fibonacci's before, or the Fibonacci sequence. If you haven't, it's okay. It's just a sequence of numbers, and it looks like this. So let's just ask some questions here. Here's the definition of the Fibonacci sequence, not in terms of code, right? But in terms of just the function itself. So just by looking at this, what is the base case, do you guys think? And I know you can't get the fancy notation in the Twitch chat. That's fine. But I will take your answers as they are. But this, whatever this is, it looks very similar to what we've been talking about already. Obviously, I didn't write the power one. Yeah, I think I see it. F0. F0 is base case. Isaac says f of n. F of n is the big problem. So f of n is the big problem. And the base case is almost always defined as something simple. So I'll just kind of break it out for us here. So the base case are these. And the reason that they're the base case is because there's no call to Fibonacci anywhere in these statements. So in fact, this function has two base cases, and that's okay. It has two base cases. And so one is f of 0 is the base case, and the other one is f of 1 is also the base case. Now, you'll notice that the actual function definition is down here. And notice it's got this for n is greater than 1. So as long as n is greater than 1, then it will do this. Otherwise, it will go to the base cases. And so notice here that we have two function calls to itself. Two function calls to itself. And so actually the way that I coded this, power, in general, here, I'm going to make it a specifically binary tree. This one's really easy. None to the 1, I think. So, like I had said before, when we look at this one, notice that we're breaking it down into smaller problems. And recall that 2 to the 1 is actually equal to 2 times 2 to the 0. Though I think what we'll have to do here is... No, we'll still need the num. I'm being a little ridiculous right now. So what this is a binary tree. What I've showed you here, this is obviously a binary tree, but kind of in a way, we considered these down here, we considered that, and that to be the base case altogether. And so in kind of a weird way, this is a unary tree in which we kind of don't pay attention to these side operations. And so, like I said, we'll spend some more time on this. Don't get me wrong, this is a binary tree. So we'll just leave it at that. But in general, what I would like to communicate to you guys, and we'll put it in the notes, why not, is the tree, however many function calls are in the function, is how many leaves each node in our tree will have. And so just what I mean to say here is that, like I said, don't get me wrong, that's a binary tree, but if you notice here the way that we've coded it, I only have one function call to this function here. And so this is actually a unary tree with this operation. And like I said, I was going to change it to call itself twice so that we could represent it as a binary tree in some sense. And so when we come back and look at this Wikipedia thing here, this is most definitely going to be a binary tree. And the reason is because we've got function number 1 called to itself and function number called to 2 to itself. And so we'll actually just leave it at that. I'm sure we're all sufficiently confused at this point, but I think we did a good job today. And we'll pick this back up on Wednesday. The YouTube upload will be a little bit slower today, like I said, because I'm just going to edit that part out. I'm sorry about that little hiccup. And once again, it's not a huge deal. There was no nuclear codes in there. No PII. It's just a goofy little mess up by me. If you have questions about the assignment, please just send me a message. Let's get you through the assignment and get that turned in at least by tomorrow night for the late deduction and tonight for the regular points. If you guys got any other questions, you can come to office hours. You can type it in the chat now. And that's all I got for you today. So thank you for coming to the class. Thank you for sticking with me and interacting. That's my favorite part. I love when you guys send messages. And that's all I got for you today. Let's see. CBay is offering more knowledge here. Let's see. I can use Control-Shift-I in Paint to make things easier on the eyes. Let's see what that does. Whoops. Oh! It takes like the inverse colors, huh? Do you guys prefer that? I'll do that in the future if you guys would like this. I know that everyone loves dark mode nowadays. I do as well. So I can totally do it this way too. Maybe I'll save the images that way. All right, so that's, I'll just keep that in mind for next time. you guys are welcome to go. The upload will go up sometime today, as well as the notes that we took today. So I'll catch you guys later. And I'll see you on Wednesday.